A satellite of mass 200 kilograms is placed in Earth orbit at a height of 200 kilometers above the surface. With the circular orbit, how long does the satellite take to complete one orbit? What is the satellite's speed? And part C is most interesting. What is the minimum energy needed to place this satellite in orbit, ignoring air resistance, which is a big thing to ignore, but that's what we have to do in physics. So anyway, here's the given, find, and solve. I've worked this whole problem out because I just wanted to go fast. So here's how we solve it. Let me zoom out a little bit. I decided to do part B before A, and that's okay. There's multiple ways of doing this problem. I think you can get the period first if you use Kepler's second law, third law, one of those laws, where it's, the period squared is equal to some stuff times the radius cubed. Of course, you can do that, but I like to solve it this way. First, let's figure out what the speed of the orbit is. Remember that, like, here's the Earth, and here's my satellite circling the Earth 200 kilometers above the surface with this much mass. And notice what I did in the given. I changed the 200 kilometers, it's 200 kilometers up here, I changed it to meters right away so I don't make a mistake. And then, this thing's moving in a circle, so the force is a centripetal force. So that's mv squared over r is the centripetal force. But it's also a gravitational force. It's a force of gravity, which is gmm over r squared. So you say, hey, the gravitational force is equal to a centripetal force. And of course, this lets me solve for the speed. The mass of my satellite cancels out. The radius of the orbit cancels out from here to here, leaving one r right there. And then, now you have to figure out what the radius of the orbit is, and here's how you do that. Remember, you have to take the radius of the Earth plus my height above the Earth to get the radius of the orbit. So here's the radius of the Earth, 6.37 times 10 to the 6. You just need to know that, or look it up. And then I add, look what I did here. Here's 200,000 meters, and I go, take the decimal and go 1, 2, 3, 4, 5, 6. That makes that 0.2 times 10 to the 6, which allows me to add the 0.2 to the 6.37 to get 6.57 times 10 to the 6 meters. This is the radius of my orbit. So I plug that in here, and here's the gravitational constant. The mass of the Earth is 5.98 times 10 to the 24 kilograms. And when you do that, you get the speed. 7.79 times 10 to the 3 meters per second. Okay. About, 5-6 miles per second, something like that. Now, what is the period of the orbit? Well, the period is just equal to the orbital speed is also equal to the distance, 2 pi r, divided by the time it takes to go around one time, which is the period. So the circumference of a circle divided by the period is my orbital speed. So I just take that and solve for the period and plug in my calculated values as shown here. And here's my answer. 5.38 times 10 to the 3 seconds, which is about 90 minutes. And I know that's right. So, woohoo. Now, part C is kind of interesting. Okay? Part C, we want to know how much energy do I need to add, mechanical energy do I need to add to that 200 kilogram mass to get it into that orbit. So how much energy do I need to add? That's a delta E. Delta E is equal to E final minus E initial. Okay, so let's figure out what the final energy is. The final energy is the energy that my satellite has when it's in orbit around the Earth. Okay, well, the final mechanical energy is its final kinetic plus its final potential energy. So I go 1/2 mv squared minus gmm over r. Now you can go ahead and do this because I know what v is, and I know what r is, and I know the masses, so I know everything. So I can just plug it into this and get my answer. But because I'm a little bit lazy, I decided to use a trick. Notice that this is the orbital speed squared right here. Well, I have an equation up here for orbital speed. Orbital velocity is square root of gm over r. If I square that, I can substitute in 1/2 the mass times gm over r. This is my velocity, or my speed, minus my potential energy, gm over r. Well, here I have 1/2 a gm m over r minus a whole gm m over r. I can now combine these terms, and they're equal to negative gm m over 2r. This minus this equals that. So now all I need to do is plug in my orbital radius with my masses and the gravitational constant, and I get my final energy as being equal to 6.071 times 10 to the 9 joules. So it's negative. Now I need to figure out what my initial energy is. Now this is a little bit tricky. Where is the payload? Where is my 200 kilograms at the initial condition? It's on the Earth's surface, near the equator. Now I wanted the minimum possible energy, which means I want the maximum possible kinetic energy. So here's the Earth. And the Earth is spinning on its axis. Okay. Well, if I put it up here, it doesn't have any kinetic energy. It doesn't have a head start. But if I put it at the equator, the Earth is spinning on its axis. So it's almost like if you launch a spacecraft from the equator, it's got a head start. So I'm going to launch it from the equator, so I have that extra velocity. Well, what is it? Well, what is that speed? Well, it's 2 pi r. Now, here, this r is the radius of the Earth, right? I'm not 200 kilometers above the Earth. I'm starting at the Earth's surface. So I use the radius of the Earth divided by 86,400 seconds. That's the time it takes to go around once. This is a little tiny bit off. We figured out what sidereal time was and all that, but don't worry about that. Just use this. And then we get this for my velocity. Now that's really fast. If you're standing at the equator, you're going 463.2 meters every second. That's like 1/3 of a mile per second. That's really fast. Okay, so I have lots of kinetic energy. I also have potential energy, negative gmm over r. So let's figure out what that is. My initial energy is the kinetic energy I have at the equator, 1/2 mv squared, which turns out to be 2.146 times 10 to the 7 joules. And then here's my potential energy, negative gm, mass of the Earth, mass of the payload, divided by r. And r here is the radius of the Earth. And when you do this arithmetic, you get negative 1.252 times 10 to the 10 joules. So this is my kinetic energy. Here's my potential energy. So I get this. This is my initial mechanical energy. This is how much mechanical energy my payload has just before you launch it, right here on the Earth's surface. So to figure out how much energy I need to add at a bare minimum, here's E final. This is the mechanical energy I have in orbit minus my mechanical energy I have on the Earth's surface. And now this means when I do the arithmetic here, I'm subtracting a greater negative number than this, so I get positive 6.43 times 10 to the 9 joules. This is at minimum. This is the minimum mechanical energy I need to add. Well, that is the mechanical energy I need to add to my payload, okay, to get it up there. Now, of course, I need to use a lot more energy than that because I have to have big rockets and fuel, and I'm giving off heat, and I have all this air resistance. So the amount of energy you actually need to expend to add this much mechanical energy to my payload is vastly huger than this change in energy. But this is the change in mechanical energy of my payload if it started at the Earth's surface and then we launched it, 200 kilometers above the Earth so that it's in circular orbit. And that is how you do that problem.